Applying the term drawback to Clojure is like weird because it is such a flexible language. And until you get to that point, you should be living in pain, right? And our implementation ended up being 10,000 lines of code end to end at scale, which is literally 100x less code than Twitter wrote to build the equivalent, just the consumer product.
It's hard to explain that some libraries are actually perfect. They're not abandoned. Not too much to do, actually, to improve them. For such amount of data, should we name it eventually consistent, but not instant?
If the job would involve that, like you were in some sort of programming circus where you are performing live for an audience, then that interview would be appropriate for that. I would actually choose JavaScript. I think I would choose JavaScript.
Yeah. Haven't you thought about, creating alternative core library for Clojure? Hey guys, welcome to the 7th episode of our podcast, Clojure in Product. Would you do it again?
Today we're meeting with Nathan Marz, the founder of Red Planet Labs. Besides that, Nathan is also a creator of Apache Storm, he is the creator of an open source library called Spectre, and he's the author of the book that called Big Data: Principles and Best Practices of Scalable Real-Time Data Systems.
And also, Nathan and his team created Rama, a platform for building backends at any scale with a programming model that generalizes event sourcing and materialized views.
Rama provides composable building blocks that can be combined in different ways to handle any or all the computations and storage needs for the backend, greatly reducing the amount of code that is needed.
And also, we have a question passed from our previous guest, Jonathan Sharvit, software architect at Sci-Cognito. And the question is, what's the part of Clojure, beside macroses, that you consistently find challenging to explain to teammates? So it's interesting to hear the answer. And let's begin. Map our questions and macro-expand them into real-life Clojure experience.
Hello, Nathan. And welcome. Thank you for joining us on our 7th episode of Clojure in Product. Would you do it again?
Good to be here with you guys. I'm looking forward to some hard-hitting questions.
Can you please share a bit about your background, how you first encountered Clojure, and what is actually that firstly attracted you to the language?
Well, I've been using Clojure full-time now for 15 years. I started with it in 2009. My journey with Clojure actually starts before that. I would say it started my sophomore year of college. This is 2004, so way before Clojure came out. But Paul Graham had published a post called Beating the Averages, where he talked about how they use Lisp. It was a very famous post. They talked about how they used Lisp at their startup and how that was their secret weapon, how Lisp enabled them to do things that you couldn't do in any other languages, and that enabled them to do as a business what other businesses could not do. And he talked about a direct connection between those things. And in particular, he's talking about macros, right? Like Lisp macros as being this very unique thing. So that really compelled me, especially that connection. So I became very interested in Lisp at that point. Shortly after that, I actually got to meet John McCarthy, which was an amazing experience. The older I get, the more surreal that is, that I sat with him for 2 hours. So basically I had Lisp in my head. So I was primed for it. And so then fast forward, and I had done this, I've been doing stuff with Hadoop, so big data MapReduce stuff. And it struck me that Datalog would be really good in MapReduce. And so I did a project where I actually made a Datalog compiler that would execute as MapReduce. And I very quickly saw the problems with doing it as a custom language, right? Just you want to be able to just easily have custom functions in it. And so I had to make this registration system, and it was very complex. But I had listened back in my mind. I had found out about Clojure, this list that compiles a JVM, and I thought that could be really good. Right? It seems like with macros, I should be able to make a very, very beautiful fine-tuned API. That eventually became Cascalog, and that's what I did. So Cascalog was actually my second project with Clojure, and that was the reason I started using Clojure. First, I did a smaller project just to get to know the basics of the language, but then after that, I did Cascalog, and that was also my first big open source project. Then I was kind of off to the races from there.
That's interesting. And back in 2013, you founded Red Planet Labs. with its mission to reduce the cost of building software applications. So can you please tell us a bit about those early days of the company, what you've been working on, and and why Clojure, and how it was with Clojure back then?
Well, just some broad background of Red Planet Labs. So before I started Red Planet Labs, I'd done this big open source project called Storm, right? Storm was implemented in Clojure, but it had a Java API, and it was primarily used by Java people, just because Java people are, obviously there's many, many more of them. And I kind of had a decision back then in 2013. So I very easily could have started a Storm company. I had tons of users all around the world, like begging me for support and consulting services. And that was a very tried and true model, big successful open source project, raise money and then, build premium features or whatever to monetize it. But that wasn't so interesting to me because that probably would have been about monetization. I, at the same time, was working on my book, which was about a broader subject, which was just about the theory of building large scale systems end to end. That's where I coined a term called Lambda architecture. And it's really about how you can think about building large scale systems in terms of pure functions. I had some insights there, which I realized formed the outline of a truly next generation platform for building software backends. So that's what I decided to focus on. I didn't really know the details of how it would work, so I knew it would be a research project. So that's what I started doing in 2013. We announced it for the first time last year. So a little bit over a year ago. It's called Rama. Basically, Rama is a big platform, has huge applicability. But to just summarize it very, very concisely, Rama generalizes and integrates the ideas of event sourcing and materialized views such that you can build entire backends with very diverse computation and storage needs on a single platform in much less code than it would take otherwise. The amount of less code that it takes compared to using traditional technologies like a relational database, for example, increases the higher scale you get. So as an example of this, last year, we built a clone of Mastodon, which is basically the same as the Twitter consumer product. And we built it at scale, actually able to handle Twitter scale, handling all the difficulties of that product, such as the fact that the social graph is very unbalanced, and that creates all sorts of tricky things in implementation. And our implementation ended up being 10,000 lines of code end to end at scale, which is literally 100x less code than Twitter wrote to build the equivalent, just the consumer product. So that was a big example of a true demonstration of what it could do. I'm sure we'll get more into it, but that's the very broad overview of what Rama is.
And I'm curious, for your company, Red Planet Labs, so the main goal was to create Rama, or you do some other kind of consulting work or anything else?
No, just Rama. That's the goal.
Just Rama.
Yeah. Now we do some consulting to for the purpose of helping drive Rama adoption. The thing about Rama, it has these huge benefits, but it does have a high learning curve because it is a paradigm shift. It's way different than anything that's ever existed in the software industry. And so we need to consult to help our users get over the learning curve.
So it took 10 years to build Rama from the year of foundation of your labs. Yeah.
So the first 6 years was just me, just doing essentially R&D. It was a brutal process to develop it because I had to discover the abstractions. And it was always 2 steps forward, 1 step back. And then in 2019, I had figured it out, what the abstractions were. And from there, it was just a matter of now engineering it so it can operate as a robust, production-worthy, large-scale system. And so that's when I raised money and built out the team. And then it took, 4 years of pretty hardcore engineering to make it a reality from there.
Cool. That's really impressive. Can you tell a bit more about connection of Rama project and Red Planet Labs with Clojure? So you've chosen this language in 2013 or maybe a bit later?
Yeah. So I don't think Rama really would have been practical to do in any other language. Of course, it would have been possible to build it in Java, let's say, but it would have taken a lot more than 10 years. 2 reasons for this. One is just the principles of Clojure, especially immutability helps a lot for a large project in controlling complexity and making it possible to reason about it. The second thing is that Clojure, you have a ton of flexibility for defining abstractions. And Rama, probably more than any other Clojure project ever, really relies on that. So like at the foundation of Rama is actually a new programming language, but it is defined within Clojure, right? It's like it uses Clojure macros to define the language, but it's still Clojure, right? Because it's macros, even though the language has totally different, or not totally different, but very different semantics than Clojure. This new language, it's a new programming paradigm. It's a data flow language. There's a ton to talk about there. We're actually going to publish another blog post specifically about the language in a few weeks. It's incredible that this can even be defined within Clojure. So it's based on what we call a fragment, which is a generalization of a function. Now, a function has been the core primitive in programming forever, since the beginning, right? You have other things like logic programming languages, which are a little bit different, but like the function is the core, right? What a function does is you call it with some input arguments, it does some work, and then the last thing it does is it returns a value back to the caller. So Rama generalizes that, right? So I call that call and response. You call it, and then it responds as the last thing it does. So a fragment is based on call and emit. And basically you can think of Rama data flow, this new language, as like reifying continuation passing style into a language and making it performant. So basically with a Rama operation, you don't return back to the caller, you emit to your continuation, which is given to you by the caller. And so when you're doing it this way, you can emit many times, or you can emit 0 times, or you can emit asynchronously, which is really powerful. And emitting asynchronously is the core primitive that turns Rama, that basically makes distributed parallel code no different than regular code. Everything composes beautifully. And so that's like the general idea of Rama data flow. Rama data flow is like, we expose that as like the Clojure API to Rama. Like you use this to program these large scale, fault tolerant, ACID compliant applications. But we also use it as a general purpose language to implement Rama itself. And so it's this really powerful paradigm, this really powerful language, but we're able to define it in Clojure. And it's all seamless, right? We can use Clojure from Rama Dataflow. We can use Rama Dataflow from Clojure, and we do that all the time. And this has been essential. Another example of this, actually, in terms of mixing paradigms, is Spectre. So Spectre is another library that I open sourced a long time ago. And Spectre does not have the scope that Rama does, but Spectre just makes it really easy, or very concise, very elegant, and very performant to query manipulate data structures, regardless of their complexity. Basically, the origins of the Spectre came because I was working on like the initial Rama compiler, and I was getting overwhelmed with how difficult it was to manage just information, because like the Rama compiler, like it's a language, right? So you have different nodes, represent different kinds of operations. The nodes have different kinds of fields in them. If it's declaring a constant or invoking an operation, but then a node could be declaring an anonymous operation. So it has nested within it another graph within it, and that could have nested. And to build a compiler, a lot of the stuff you have to do is like transformations across the entire abstract graph, right? Which could be like deeply nested. And that was like nightmarish to do with just vanilla Clojure. Like so much boilerplate and overhead to handle the iteration, and et cetera, et cetera. And so Spectre came out of that as a very elegant way to deal with nested data structures. And then it grew to be more than that. Spectre is not only like critical for implementing stuff like the Rama compiler, but it's also part of the Rama API now. It turns out to be an amazing API for dealing with durable indexes. Durable indexes in Rama are just nested data structures of any size. Cool thing about Spectre is that Spectre outperforms Clojure itself on equivalent operations. So like you compare like calling get in, right? One of the core Clojure library functions, and the equivalent code in Spectre, it's the exact same thing. It's just a different name, right? But the code is essentially the same. And Spectre is 30% faster than Clojure. But we're able to do this within Clojure. Like that's the magic of Lisp, is that you can mold the language. You can mold the language itself, right? Because you can build abstractions which are as good or better than what the core language provides. And no other language besides the Lisp family that capable. And so that is something we leverage a lot.
And what is correct term to describe Rama? Is it framework? Is it library? Is it language? What is it?
Well, I would call it a platform. But you program it as a library, right? So it's not, there's no like custom languages or anything. You can either use the Java API to program it or the Clojure API.
But you mentioned that you have an idea to rewrite Rama in Rama itself.
No. That's Rama is already written in largely in Rama in the Rama language. Yeah.
It's very, very, very unusual because we usually have people that build some systems, and you actually have a lot of contributions into open source and into this platform. Do you have an idea, or do you have already some production cases of usage Rama in real life?
Yeah, we're currently in private beta, so we haven't publicized anything yet. So we're using the private beta as an opportunity to, first of all, get some users in production, of which we have many, and also use their feedback to improve Rama. So a lot of the work we've been doing has been based on that feedback. And a lot of it's like little improvements, API improvements, and other things are like big new features. Yeah, it's been very successful. The most interesting ones are the ones that rewrote their whole platform, like their whole application on top of Rama. So we have one that did it. And I think this is something we're consistently seeing, that even at small scale, the Rama version of the code ends up being about 50% less code, which is interesting. This was a Clojure company that did this. I think like that is interesting, but I think like even more impactful is just the reduction in complexity, right? So essentially what Rama lets you do is, rather than having to twist your application to fit your backend tooling, to like fit this data model of your database, which is fixed, right? You can't do anything about that data model. Rama lets you mold your infrastructure to perfectly match your application. So you get rid of all of the impedance mismatches, which traditionally exist, right? Like, for example, something like an ORM is pure complexity, and it's a way to deal with an impedance mismatch, but it doesn't really deal with it because it leaks and it creates a lot of problems, as people have discovered over the years. So Rama completely avoids all those problems because, and just to give like one aspect of that, right? I talked about like molding your infrastructure to fit your application, right? And I mentioned databases, right? Databases have a data model, which is fixed: document, graph, relational, whatever, right? Now, a data model, it's really just data structures, right? It's just a particular combination of data structures. Document is a map of maps. Column-oriented is a map of sorted maps. Graph is maybe two, one for nodes, map of maps, and one for edges, right? Whatever, right? And so what Rama does, it lets you define all of your indexes, your materialized views, like literally as data structures. But they're durable data structures that can be of arbitrary size. Even your nested data structures can be larger than memory. That's something called sub-indexing in Rama. And so you're able to define your indexes in exactly the shape that's optimal for your application, right? Maybe and you find as many of them as you want. So maybe for this one use case, you want a map of sets. Maybe for this other use case, you just want a single number, right? That where one exists in every partition. Maybe for this other use case, you want a map of sorted maps, of lists of maps, or whatever, right? It completely depends on the use case. And so that's a really powerful thing in that. That's what I mean. You're able to mold your infrastructure to fit your application rather than the other way around.
And I'm curious about the largest installation of Rama that you have in production. Maybe you can name some numbers, how many terabytes of data, events, views, because, if we talk about production usage, I can imagine that these materialized views should evolve a lot. And sometimes we need, for example, to reconstruct the data from the very beginning of the history. And I'm curious how it really works in production.
So our users range from less than 1 event per second to like about 1 million events per second. The one that's at 1 million isn't quite in production yet, but Rama is able to very easily handle that throughput because it is a scalable system. Yeah, you brought up an interesting point, right? Like being able to recompute views from scratch. And that is something our users are doing. And so that's something that's very powerful. That's something that's enabled by event sourcing, right? So the Rama programming model is, so event sourcing means that rather than directly modify your indexes like you do with databases, where like you modify the current state of the world and then that's permanent, you actually keep a log of all the events that happened, and that log is immutable, and then you materialize these views on top of it. And with Rama, you materialize that incrementally by programming these things called topologies. This is what you use Rama's Dataflow API to do. And there's a few different kinds of topologies, but basically they incrementally materialize the views, right? And you define how do you go from depots to these views. The views are called P states, which means partition state. And so when you have your whole history of everything that happened, you have the ability to recompute your view if you need to. And that's a really powerful thing. That's something you don't have. That's a big thing that you don't have when you use a database, like a relational database. And we have seen, and it's interesting to us that we see our users doing that on a pretty regular basis. Sometimes it's because they actually they deployed a bug, right? And so they've essentially corrupted their P state, but they can fix the bug and recompute it from scratch. Other times it's just they have a new feature that they want to do, and they'd like it to be historical, but they already have they have the data on their log called depot, and so they can just recompute it from scratch. So that's been a really cool thing to see, just to validate that that's such a useful thing that even our early users are doing it so frequently. We're actually doing a new release today. I'm going to do it shortly after we finish, but we made something. We made a migrations feature. So recomputing a new view from scratch is great, but it can take a while, right? What migrations lets you do is, just like you do with database migrations, just modify your existing view in place.
I see.
What's really cool about our migrations feature is it's instant. So even if your view is 10 terabytes, the migration's instant. You just click a button and boom, it's immediately instantly migrated. The way it works is that so some migrations you might do would be like, let me just change the type of this value within this view, right? Like change it from an integer to a string or something. That would be like a very basic migration. And the way it works is that you provide like an arbitrary transformation function of how do you want to like modify these targeted values. And what we do is we apply your transformation function on read, which is why it's instant, while we slowly and durably migrate on disk in the background. It's really cool that it's instant because this is something that just hasn't existed before. If you ever tried to do like an alter table on like a really big like relational database, you have to take downtime. Like that's unacceptable. Like you might not even be able to do the migration. And so you might have to just do something much more complex, like have your application able to handle multiple versions of the values within it. It gets like very crazy. I've had to do that before, and the complexity gets insane. And so this instant migrations thing, essentially, it's a big leap forward because now you can deploy these huge migrations and not have to worry about it.
But for such amount of data, should we name it eventually consistent, but not instant?
No, it's instant. It's not eventually consistent. It's immediate. Anyone reading from that view is going to see the migrated data. Now, the fact that it's not migrated on disk yet does not change anything about semantics.
I heard a lot about in the Clojure world about working with data with event sourcing style, handling this infinite persistent log of events, building the views on top of this. And maybe this question is stupid, but can you compare Rama with Datomic and its approach? Because it sounds kind of similar for me.
You don't really control how stuff is indexed at Datomic. Datomic, you have, it indexes it the way it does, and then you're able to query ranges of that data onto your peers. So that's a huge difference. Rama, like Datomic, has a data model, and you have to conform to that data model. You have to put data like that, and that's all it can do. Datomic's a great system; it's very flexible, but it doesn't have the capabilities of Rama. There's like smaller things, like Datomic is not scalable on writes because it has a single writer thread. Rama is fully distributed; writes happen in parallel and distributed. So they're quite different. There's another product called XTDB, which is, I guess, similar to Datomic. So actually the user I mentioned that rewrote their application from scratch to be on Rama, they're rewriting it from an XTDB based application. We could go through like feature sets, right? But like there's like huge differences in like reactivity and stuff like that as well. But in terms of big picture, like Rama very explicitly makes a difference between event sourcing, which are logs, and that's stored one way, and materialized views, which are stored another way. And they're both durable and they're separate, but they're connected by your topologies.
I see. Very interesting. Returning back to choose of Clojure for building such system, can you name some drawbacks or problems that you faced by working with Clojure? You faced already one about Spectre, that vanilla Clojure doesn't allow to work with complex nested data structures. Maybe something else that you found on your way?
Yeah, well, applying the term drawback to Clojure is like weird because it is such a flexible language that you can essentially change the language like at the user level, right? So they're not really drawbacks in that respect. I do think Clojure has some weaknesses, and the more experience you get with Clojure, the more you understand those weaknesses, and then you can deal with them. So Clojure's interesting, especially with performance. And this is an area where we've had to do stuff to handle, I guess, so what we consider to be deficiencies in Clojure. And this is not a criticism of Clojure's design, because like no language is going to be perfect, right? So for example, like lazy sequences, I do not think that should be part of the core API of Clojure. That there should be like a namespace, Clojure.lazy, and it all should be in there. But the default functions for map and filter and whatever should be eager. So the problem with lazy sequences, they add a lot of overhead, even if you are like fully realizing them. So they're slow. And even worse than that, if you're not fully realizing them at the call site, if there's an exception, it actually, and I'm sure you've experienced this, it moves the exception somewhere else, and it's really confusing to debug. We actually do use lazy sequences legitimately for laziness. I think it's in 2 spots in our entire code base. Our code base is about 200,000 lines of Clojure, just the source code, right? We have another like 250,000 lines of tests. So in that whole code base, we use laziness twice, and we call, or we do those operations, mapping and filtering, all the time, right? So almost every single call, 99.99% are eager, and we want them to be eager. We absolutely do not want them to be lazy. We use Condo for linting, great tool. And so we lint to just disallow, our build fails if you use any lazy functions, because there's just no reason to. Doing the eager version, using map v instead of map, is no more work, but it's better, right? It'll be faster, less overhead, and won't have this issue with stack traces. So that's one issue. But again, not really a drawback because you can deal with it. It actually is something I find odd about the language, how it is both very focused on performance, but then other times it seems to just not care at all. So like protocols, transients, these just like the implementation of persistent data structures are fantastic. These are fantastic high performance features. But then you have other stuff like the function satisfies. Another thing we lint for, just don't use that function. Instead of using satisfies, what we do, and we have to do stuff like that, but instead we call extends on the class. Because it turns out the cases where we use it, we're directly extending it anyway, such that it's equivalent for those cases, right? Satisfies is like ridiculously slow, and it could be faster. It could use inline caching, whatever, just like protocols do, but it is like super slow. Like it's frustrating to be looking at a performance profile, and it's like satisfies. It's like using up like all the CPU. I won't even mention last. I strongly disagree with the design of last because it's always linear time. It's always O of n. I've read Rich Hickey's rationale for it. I disagree with that. I think it should be as fast as possible on the data structure it's running on. But fine, he has a rationale for that. But then you look at first. First is O of 1, but it's a slow O of 1 because it goes to the lazy sequence API to do first. So there's a ton of overhead. So in a lot of places in our code base, we have to not use first and use a faster version of it. So I would rather, like, we wouldn't, if Clojure core library made all the functions as fast as possible, we wouldn't have to do stuff like that. And so that's a little bit frustrating sometimes, but you learn and you can deal with it. These are not like fundamental deficiencies. These are small deficiencies that you can deal with, but it is part of the learning curve for building, high performance systems in Clojure. This stuff doesn't matter if what you're doing is not performance intensive, but it matters a lot for us. Oh, another interesting one I just thought of is, and again, we were able to work around this, but one of the most common sources of bugs we had in our code base was just like a typo on accessing a field of a record, right? Like the field is named value and you misspelled it for some reason, right? And Clojure would just return nil, right? Because like records are open. You can access whatever you want. But it turns out with our records, we never use open fields. We always only want to use the fields that are in the record. So we made something called def record plus, which will actually throw an exception if you try to access another field. And that has totally eliminated that class of bugs from our development, which has been really nice. Again, it's an example of something we find Clojure's design for records is not great when you're actually trying to use it in a complex code base, but def record plus looks exactly like def record, and it fixes that problem for us. So again, we're able to mold the language to be more optimal for how we're using it.
Haven't you thought about, creating alternative core library for Clojure? Because some languages have different implementation of a standard library.
What do you mean? Like actually making like Clojure.core too and just re-implement?
Yeah, kind of this. I know. Clojure.core.performance. I know.
Yeah. I mean, I think people have done stuff like that. Like those are like utility libraries. I think most of the core library is fine, right? It's just like a few functions which are bad. A lot of this learning about doing stuff like as efficiently as possible is actually baked into Spectre, right? So Spectre is like, as I mentioned, is very, very high performance, though. For something as like basic as just calling first, like Spectre does add a little overhead, so it's never going to be as fast as like directly calling a faster version of first. I don't know about releasing another core library. I think that like the core library, like that's the core of the language, right? Like you're not going to really replace that.
For C, sometimes we can use different implementation of std.lib. So sometimes it works.
Right. But you can't actually replace the core library in Clojure. It's always baked into the jar.
As you mentioned, you continue to develop and improve Rama itself as a technology. Can you think of what maybe lessons have you learned about building larger scale systems with Clojure that you think are critical for other developers to consider and understand?
Yeah, we actually a few years ago did a post about this. It's called Tour of our 250K line Clojure code base. Now it's more like 450K lines. But yeah, a lot of stuff we wrote about in that post, I think, does apply to learning just like things we learned about managing a code base of that size. That's all in Clojure. So I think one thing that's really important is just how you manage like types and schemas. So I started working on Rama like way before Spec was released. So very early on, we started using this library called Schema from Prismatic, and we still use it, right? And I think Clojure.spec is good, and I also think Schema is good. So we just continue using Schema because we had no reason to switch. But I do think making your types tight, like tightly defining what are your types and what are like the fields within them is important. And because everything's dynamically typed, you can do things besides just like a type. You can do stronger things like predicates, right? Like this value is not just a number, but it's between 0 and 10 or stuff like that. And we do stuff like that all over the place. And I think it's important. It's like little things that are important. It's important when you're doing this to actually validate the types that you're creating. So this def record plus thing that I mentioned. So besides the fact that it has this functionality to disallow accessing undeclared fields, it also has schema defining built into it. So when you define your fields, you say, just like with Schema, you define what the types are. And it generates a bunch of constructors for actually constructing the type. So if we create like a def record plus on foo, we don't construct it by using like the record constructor. We have something called valid foo, and that will actually do type checking. So on construction, it'll throw an error if there's any sort of schema mismatch. And we integrate it with assertions, so we're able to like do it so that it only does those checks on if assertions are on, so that we catch those things in development, but we can turn assertions off for our production release so that you don't have the overhead of those assertions in production. Because those assertions are just catching development time problems. So that's really important, right? And then, you need to think about in your code base, like where do you actually check schemas? And it turns out in Rama, like besides construction of types, there's a few like central places in the compiler where it makes sense to like do some schema checking just to make sure everything's fine. So that's a big thing, right? I think something for like programmers that come from like a statically typed language, whether it's Java or something else, dynamic typing scares them, right? Or they think they're losing something by not having static typing, when that's absolutely not true at all. Once you learn how to do it, what you're losing is complexity, the complexity of static typing, and you're gaining a much more powerful type system because you can do much more things dynamically than you can do statically. But you have to learn to do it. And I think it is a very, very critical part, especially as the code base gets large.
I have a question regarding the schema usage, because we have the question from one of the previous guests, and he asked about usually schema is used on the boundaries of the system. So we get from external API some request, and we need to validate it against schema. Can you tell a bit more about how deep inside the code base are you using the types, and or you're using it on the boundaries? You mentioned the core of the compiler. It's also interesting where exactly are you validating these types?
Yeah, I find it useful to basically default to when you declare a type, a new type, you give it a schema. So it's basically everywhere. And like you can think of it as like within a big system like Rama, well, there's lots of internal boundaries, right? You have workers and task threads. You have replication. You have depots and p states and whatever, right? And within the compiler, you have many different kinds of operations in the compiler, which would be different nodes. And the thing about like the problem with not putting a schema on things is that when you mess something up, I use the word when, not if, because you are going to mess things up. If you're not catching it at the time you created a type, it is so much harder to debug and track it down. You always, in all situations in programming, you want the error to happen as close to the source of the error as possible. Otherwise, it just gets, the further it is, the more difficult it is to figure it out.
Answer is everywhere.
Pretty much, yeah. I mean, I don't think we use it literally at 100%. There's probably like very localized places where it's like purely internal to one function, but pretty much everywhere, because it doesn't add overhead. It doesn't like make it more difficult to develop. Okay, you got to spend a second annotating the types. So it's like, all right, this is a string, this is a long, I'm done, right? And then instead of using the normal record constructor, you use the validation constructor, which is just a few more characters. And that's it.
As I understand, this checks is always on, even in production builds.
For the Rama releases, we turn assertions off. And so those checks will not be on. But we're talking about things that are internal, right? So it's important that we catch these problems during development. It does use CPU to do these checks, so we turn them off for the production release.
I see. And as I understand, for these checks to properly work, you need to have a pretty extensive test coverage of the code base. You mentioned that you have pretty similar size of tests like the main code base. Am I right? Yeah.
Yes.
Do you track some coverage of the code base by tests? And maybe coverage by schema? That's also interesting. But I think it can be done with CLG Condo or something analyzing.
Yeah, we don't test cover or like code coverage metrics. You mean like actually measure how many lines of code are exercised?
How many lines, maybe, at least.
Yeah.
Not branches.
We don't specifically check that. It's not a bad idea for us to do something like that. I was also looking at something like even more interesting than code coverage called mutation testing. Might not be, I don't know if you've heard of it. It might not be practical, but the idea,
I heard.
Yeah. Mutation testing, it's a great idea. The idea is that if you randomly modify your source code, what's the probability that your tests fail, right? That's the real metric of coverage, right? Just because you're exercising the code doesn't mean you're testing all the different things it needs to handle. Now, mutation testing, especially with something like Rama, is going to be tricky given that we kind of have to build that ourselves because it's like existing tooling is not going to understand Rama code at all, right? Like what's a valid like mutation that it can do and whatnot. And there's questions about like what kind of mutations can it even do? So anyway, I don't think that's actually practical, certainly not in the short term for us, but interesting idea. It doesn't matter what tooling you're using, testing is important, right? Like a lot of people from statically typed languages think that static typing reduces the amount of tests you need to write, and that's completely false. Like 100% absolutely false. And so nothing changes. But yeah, something like Rama, as it's gotten bigger, the rate at which we write test code versus source code has increased. So right now it's, I think, 250,000 lines of test code versus 200,000 lines of source. I'm expecting that discrepancy to only grow. Like Rama is it's a large, complex system. And it needs to provide very strong guarantees. It needs to be able to operate under very bad conditions. So a lot of our tests are doing stuff like chaos tests, where you do stuff like kill workers randomly, partition workers, and so on. And the system needs to keep on working. There shouldn't be any insertion errors. It should maintain all its guarantees around durability and atomicity and so on. So most of our time is spent doing stuff like that. And that's actually talking about strengths of Clojure. Clojure is very strong when it comes to testing because of the way you can use the language. So like as an example of this, there's one technique we use where we use with-redefs a lot in tests. And now sometimes it's to do something like it's essentially dependency injection, right? Mock out this internal function and have it do something different. And that's fine. And it's very easy to do that in Clojure. But the more interesting usage of it, and we wrote about this like a couple of years ago, is we will put into our source code no-op functions. And we always, we have a naming convention, so we always prefix it with hook : right? So it'll be like hook : finished replicating entry or whatever. And the definition is just empty. Defin that, and then that's it, right? And what we can do is, what that essentially provides is an a la carte event log on everything happening in the system. So we can do with-redefs and actually capture the events, and then we can assert on those. So it's a really powerful technique, which is just a really unique way to use Clojure's facilities. Also in a way, it's like almost no code. It's very powerful, very simple. And that's been like a very useful technique for us in testing this thing.
Very interesting technique. I will apply it to my code base because I use hooks, but in a bit different way. But these empty definitions are pretty good.
And with Rama, we can do like even cooler stuff with hooks. Like one thing we do sometimes, we'll do a no-op fragment, right? So it's just essentially a fragment that takes in no arguments and then it just emits one time, right? So when you call it, it does nothing, right? It immediately comes back. But we can actually redef that to become asynchronous. So we'll like introduce essentially a yield or a pause into some code, and that lets us test especially certain race conditions that could happen by being able to inject these yields in a place which normally would not yield. That's beyond Clojure, but that's something very interesting that we do pretty frequently.
Are you using core async in Rama?
We do not use core async in Rama. Essentially, Rama itself is able to do the kinds of things you would do with core async, but it's more powerful.
I'm curious about, it's not about maybe only technical stuff, but also about cultural stuff of Clojure engineering team. Sometimes I've seen cases of over-engineering something because Clojure is very flexible. It allows to do a lot of things. You can build DSL, you can use macroses, you can build embedded DSL using macroses, and you can create your own language inside the Clojure. Have you faced maybe some cases of over-engineering that you need to maybe manage even now, or you already refactored this?
Well, I wouldn't say over-engineering because I think we're just we're a strong team. Like we know what we're doing. I mean, the philosophy that I follow with development, which helps a ton in avoiding over-engineering, is basically don't build abstractions unless you have a really good reason to. So when I say something like we built our own new language, implementing a brand new novel programming paradigm from scratch, I did it because I had to. It wasn't something that sounded cool, so I did it. I did it because I had no other choice. I had no intention of building a new language when I started working on Rama, nor did I think I needed to, right? It just turned out that I was forced to do. You should always feel forced to build an abstraction. And until you get to that point, you should be living in pain, right? because you don't have that perfect, beautiful abstraction yet, right?
Mm-hmm.
You follow that approach, you are going to avoid a lot of the over-engineering that a lot of people do. Now, of course, we have technical debt. Anyone working on any sort of system over a long period of time is going to develop technical debt, and I don't think this is unique to Clojure. Now, you do bring up a good point, though, right? Because Clojure is a much more flexible language, it gives you more ability to shoot yourself, and that is true, right? So I do think you need to be a more skilled programmer to work in Clojure. I would say it has a lower floor but higher ceiling, right? I'd say it has a much lower floor and a much higher ceiling. If you're a good programmer, if you're skilled, then you're able to hit that higher ceiling without going to that lower floor. And so like something we do in terms of technical debt at Red Planet Labs is we dedicate 1 day a month. We call it Sweep Rama. To all we do in that day is address technical debt. Right. Cool. So there's actually like some nice things about doing it this way, but we basically keep on our Jira. We have a label called Sweep Rama, which when you encounter something that could be better, like this could be refactored, this naming could be better because it's confusing how it's named currently. We're able to just punt it, just open up a Sweep Rama ticket for it. And then we can all get to it as a team when we get there. And that's the kind of stuff we do, right? We clean up code, we rename things, we factor stuff out. And so when we've been working on Rama as long as we have, by just doing this once a month, being diligent about it, we're able to keep the code base like clean and elegant. But I think this is true regardless of what language you're using. Like you have to explicitly think about tech debt and how you're going to combat it.
I have a question. You mentioned it quite a few times by yourself that. Rama is a like complex tool, and that you have to have a really strong engineering team in terms of building something like Rama. So I'd like to ask you about the team behind Rama. How big is the team? What is your role within the team? Like, how involved are you personally into the like coding day to day?
Well, the team is 5 right now, so we're a small team. I mean, most of my time I spend on development, right? So we're all developers. We don't have anyone besides developers in the team. I'm leading the engineering as well as, handling all the other stuff that goes along with running a startup.
Also, one more question regarding this. So due to its nature, Clojure normally attracts really experienced engineers with varied experiences and approaches. And when you have a bunch of experienced engineers sitting in one room, it's both challenging and rewarding. So how do you approach like the tech decision process within the team to ensure the smooth cooperation and collaboration within the team?
We're not all in one room because we're a fully distributed team, but metaphorically, we're all in one room. The way we approach development is that whatever your project is, you own it and you own the decision on that project. And you should use your, the rest of the team, including me, as necessary to make the good decisions there. So like one thing we do there is in terms of the development process, whenever you're about to embark on like a bigger project where there's like design flexibility or there's choices to make in the design, we use something called a pre-mortem, right? So you just write up just briefly, what's the project, what are the risks, and what are your initial ideas on how to approach it. And then on the next team meeting, we'll all look at that and talk about it together and give feedback. But otherwise, it's your decisions to make. That's worked for us. Now, mistakes have been made where after the fact, we see that that wasn't the right way to approach the design. But then we have to just go and change it, right? And that's worked for us. And especially if you're on a strong development team, if you're good, you're going to listen to the feedback that you're getting. And if you're not listening to other people's feedback, well, you're not going to be an engineer at Red Planet Labs. I've worked with people in the past at other companies which were like that, and I just wouldn't hire people like that. Yeah, I guess that's how I would answer the question. It's not particularly innovative, but you just hire good people, and we just have very simple processes in place to provide feedback.
I'm wondering, how do you approach the process of finding right people? So you mentioned it yourself. It's not an easy task, given to attention that you basically will be working with this person day to day on your own product, on your own technology that you'd like to develop. So it's important to qualify the person for the position. How do you do this?
It always has been and will always be the most difficult part of running a company is hiring. Clojure is interesting because it's a much smaller hiring pool, but it's also like the average Clojure programmer is much stronger than the average programmer. So that compensates for that. And also Clojure programmers generally really care a lot about working in Clojure, especially working on something like Rama, which is a really interesting project. The fact that you can also do that in Clojure is a very rare opportunity. Basically, sourcing candidates has never been a problem for us. Still, finding a good a good person to hire it's always been difficult and frustrating. We have a pretty tough interview process. It involves 3 take-home projects and a number of interviews. And honestly, even with all that, it's not perfect. Like I wish there was a better way. The only way you really know how good someone's gonna be is when you work with them. You know, like what I care about with people we hire is like you have a mentality of getting things done, which unfortunately, I would say most people do not have that, even if they think they do. You do whatever it takes, you're resourceful, you just get things done. Like Rama, like working on Rama, I talk about how using Rama has a learning curve, but I'd say it takes like 1 or 2 weeks of using Rama before you get over that learning curve, right? Working on Rama has a much, much bigger learning curve. Like we have very advanced systems we've developed, especially with how we test Rama. We didn't talk about simulation at all, but simulation is this like incredibly powerful testing framework that we've built to test Rama. And learning how to use all this stuff and learning how the Rama code base is structured, all different components and all different ways you can manipulate it, especially in a testing context, is a very, very high learning curve. Basically, my answer is that I don't have the answer for how do you hire great people consistently. I think with the take-home projects we do, it's a hell of a lot better than doing a live coding interview. Because if you're doing that, you're basically essentially just hiring at random. If you're considering someone, or if like you're putting a lot of weight into someone's, the school someone went to, it's even worse. And so at least our take-home projects, we're at least having them do something which is related to the job they're going to do. It's like doing like a live coding interview. It's like, it has nothing to do with the job at hand, right? It's a toy problem with the time pressure of having to perform to someone live. If the job would involve that, like you were in some sort of programming circus where you are performing live for an audience, then that interview would be appropriate for that. Otherwise, it makes no sense whatsoever. Even take-home projects, I feel, because a take-home project cannot be that big in scope, it's a better measurement, but it's still not a perfect measurement and it has noise. So basically, I wish I knew a better way to hire, but I don't. And I don't really know what other tools are even potentially at my disposal to use. But the only other thing you can do is like a work trial, but that's not possible. That's only very rarely possible because usually when someone's interviewing, they're currently working somewhere else. So they literally can't do a work trial. That's certainly a better way to hire, but it's a very rare thing that you can do. So
yeah, that's actually interesting thought. I agree with you. It's I've been participating in numerous interviews that been involved with live coding, and I've seen when really experienced guys in Clojure, but not only, like in JavaScript, in Python, they were really good engineers, but because of the time pressure of the necessity to explain yourself to another person while you're doing something, they were just unable to actually to perform the task just because of that. If you would give them this task in a normal day, just as a task on a Trello board or in Jira board, they would just complete it in 20, 30 minutes. But because of these other factors, it's just getting harder for them.
I've seen the same thing. There's very strong engineers who, like, they look like the weakest. They look like they've never programmed before in a live coding interview. And it's just shows how bad that process is, because they would be a very good hire. Your measurement has so much noise associated with it that you would actually very wrongly filter them out.
Actually, approach that I really kind of like is not when you're trying to ask some deep questions about I don't know, Clojure or JavaScript or anything else, like, some academic level questions. But when you give a theoretical task to an engineer, not a coding one, just a theoretical, and you have a conversation with an engineer and try to hear how the engineer would approach the task, what are his thoughts on this or that, and basically have more like a conversational one interview. And this way, you kind of test out how can your real work with this person will play out at the end, because it's the part of your work with such an engineer.
I do that a little bit with take-home projects. I'll talk with them afterwards about how did they approach it, right? It's very fuzzy though, still. I do think that like ultimately it comes down to just being empirical about it, right? Whatever your hiring process is, and it's amazing that so many larger companies don't do this, but actually track some stats about how people did on their interviews and then how are they as employees later. And that will tell you something about your hiring process. And most people don't do that. And I think any sort of idea you have for another way to measure how good someone is, well, you should also try to measure your process, be data-driven about it. And if a company is doing that, it won't take long for them to realize that live coding interviews are completely useless.
More importantly, have your own engineers try those live coding tests that you are putting the candidates through. Because we actually had such case with our partners. So they've been trying to find engineers in-house, and they've been like, all the candidates were failing just because they were unable to complete the task. And so our partners tried with their own in-house employees to pass the test, and they failed.
I believe Google has done that multiple times, and then other large companies. I actually don't know. Does Google still do there's crazy live coding interviews?
I know there is about 6 different interviews you have to perform. It's a really long cycle, but I don't know specifics.
Yeah, I'm just wondering because they have found that exact thing, that their own engineers were failing their own interviews. And I don't know if they actually adjusted their hiring process, though.
That's interesting. But yeah, I totally agree with you. So the best way is to basically actually have engineer work with you on real project, and pass some time, you will eventually understand whether it's the right person or not.
Yeah.
That's pretty interesting to hear your thoughts about team building. And that's always a question, especially in the Clojure. And I want to go back a bit into technical questions. And I want to ask you about how do you assess the current state of Clojure ecosystem? So 2024, plans, conferences, libraries, everything else. Do you think Clojure is growing, or it's stagnating, or it's declining?
I'm not really that in touch with how much it's growing or stagnating, right? And because it doesn't really matter for me personally, right? For me, Clojure is by far the best language to use to build what we're building. I think the ecosystem is great, though. Like tooling that exists now that did not exist 10 years ago would be like, a big one is CLJ Condo. That's a great tool. And linting is a great thing to add to your development process to just improve the code that you're doing. Like we lint for all sorts of stuff to keep our code like clean and consistent, right? Like I mentioned, doing stuff like disallowing certain Clojure core functions because they're so slow. We do other stuff, right? Like we ensure that the same namespace is always aliased the same way across the whole code base, and that we never use the same alias for multiple namespaces. And that helps a lot with code readability. You see the alias, you know exactly what it's going to refer to. And then tons of stuff like that we do just to keep the code consistent. There's a lot of interesting stuff happening in Clojure. Like besides Rama, like another interesting tool is Electric, really interesting front end tool. And they're trying to push the boundaries of what's possible with front end tooling, like similar to how Rama is pushing the boundaries of what's possible with back end tooling. Some of our users are using both Rama and Electric, so they are really on the cutting edge. And so I think it's really cool, and it's really good for Clojure that there's such innovative stuff still happening within or using the language and within the language. I'm very happy with Clojure, and the nice thing about technology like this is that it doesn't really matter who else is using it, right? If it's good, it's good, and you can use it. It's not like a social network where it matters a lot who else is using it, right? That's actually the entire value of the system. If the technology is good, you can use it.
Sometimes this is kind of objective for people outside of Clojure ecosystem, that a lot of libraries are not updating very often. A lot of libraries are kind of abandoned, but it's hard to explain that some libraries are actually perfect. They're not abandoned. There's not too much to do actually to improve them.
Yeah, like the open source Spectre library. I think it's been years since there's been an I've updated that. I just haven't. I haven't had to. I did merge in a pull request 2 weeks ago, but that was the first one in like years. It didn't need any updates, right? It was like fine. It was fine. And so that's not really a big deal.
The last question from our podcast is actually, would you do it again? Would you choose Clojure if you would start in 2024 for your project?
That's really crazy. If after everything I just said, if I said no, I would. No, I would actually choose JavaScript. I think I would choose JavaScript. Of course, I would choose Clojure again. There's no doubt about that.
We need this part just to make teaser.
Right.
Because not everybody will listen to this point of interview.
Right.
Actually, we have question from the previous guest, Jonathan. He's software architect at Sci He asked, what the part of Clojure, aside from macroses, that you consistently find challenging to explain to teammates?
Aside from macros, that's interesting. Yeah, I'm thinking about what for new employees that start up, what's like the most challenging things in Clojure for them. The thing is, like, the people we hire generally are already pretty experienced in Clojure by the time we hire them. I mean, there's like more advanced stuff with, it's still macro related, but whenever you have to use like, like the special env and form stuff, that's something most people have never encountered, and we've had to do some stuff with that. Oh, I got a pretty esoteric one for that, which is a lot of stuff we do in Rama is like a big part of how Rama works is we serialize functions. So we'll like serialize an anonymous function to actually be able to send it over the wire. And what we do is we send over the wire the class name of the function and then a serialization of the closure. Yeah. And so that part of the code base is very much relying on internal knowledge of how Clojure works to be able to do that, to be able to then reconstruct it on the other side. So that's, I'd say, for new employees, if they ever have to encounter that code and how that works, that requires some explanation. I don't think any other company has ever had to delve that deep or actually utilize that kind of information within Clojure about like the specifics of how Clojure generates classes such that we can serialize a function over the wire.
So you basically capture the context of a function, the code of the function, and you send both of them.
Right. It relies on both sides, both the sender and receiver, having the same compilation so that they have the same class names, because Clojure will actually randomize, especially for anonymous functions, Clojure gives it a randomized class name. So this relies on both having the same class name. And then understanding when you actually look at the class itself and look at the fields, actually understanding how that's going to translate to the constructor for the anonymous class.
You wrote this code, or one of your engineers?
One of my engineers wrote it like many years ago. This was like, we first did this like I think probably 3 or 4 years ago.
Thank you for response. So the most complex part of Clojure is serializing functions with a Clojure. Everything else is simple and easy to understand.
Yeah, well, it's a difficult question to ask someone who's very experienced in Clojure, who's gone through the learning curve so long ago, and who hires experienced people already.
Yeah, I agree.
We don't get tripped up by transducers or transients or all that other stuff that might trip up a new programmer.
Yeah. And you can ask question for the next guest.
Oh yeah. All right. So for the next guest, I'll ask, what's the last time you spent all night working on a Clojure project?
Nice.
Thanks for the question.
on Friday, I think.
Nice. I'm glad to hear that.
Till 4 a.m. That's not the whole night, but the big part of the night.
Yeah. My last time was a couple weeks ago debugging something.
Thank you very much for joining us, Nathan. It's been truly pleasure. And thank you for sharing your insights and your path with Rama, with building the scalable platform, that actually the platform that helps building scalable solutions. It's really an interesting story of Clojure in the product. And I'm sure that our listeners, they will be interested to hear about your path. Thank you very much for that.
Yeah, nice talking to you guys.
That was really interesting. Thank you, Nathan.
To our listeners, if you're curious to learn more about Rama and the Red Planet Labs, we'll be including links to their company website and social media. So yeah, please be sure to check them out.
Thank you, Nathan.
Cool. All right, take care, guys.
To the audience,
Thank you.
See you next time. Bye-bye.
Until next time.